Good evening, everyone. I'm here to share with you my next lecture on arenes. This is going to be a long lecture, so please be patient. Now, what is arenes? They are also known as aromatic hydrocarbons. So, hydrocarbons are based on the benzene ring as a structural unit. So, these are some examples of arenes: benzene, methylbenzene, ethylbenzene, alkyl benzene, and naphthalene. The term aromatic was used because the first benzene-like compounds isolated do have pleasant smell. However, the vapors are toxic, so please don't smell them. Aromatic is retained to indicate certain chemical characteristics rather than odorless properties. So an aromatic compound has special stability. Benzene is more stable than triene. Aromatic compounds are benzenes, and those compounds possessing the ring structure of benzene or other molecular structure resemble benzene in structure and chemical behavior. These are the nomenclature of benzene derivative, which include mono-substituted benzene derivative. The name of the substituent group is added as a prefix to the word benzene. We have methylbenzene or toluene, ethylbenzene, nitrobenzene, and chlorobenzene. Other derivatives have special names which show no resemblance to the name of the attached substituent group, like benzaldehyde, phenol, phenylamine, benzoic acid, benzene sulfonic acid. So the benzene was removed from the naming. For di-substituted benzene derivative, the numbers are used to indicate the relative positions of the two substituents, like 1,2-dibromobenzene, 1,3-dibromobenzene, and 1,4-dibromobenzene. So for this, we call it auto, meta, para, OMP. If the two substituent groups are different, the name of the group prefix benzene in alphabetical order. For example, 2-bromo-ethyl-benzene or 1-bromo-2-methyl-benzene. That is also fine. We can call this 1-methyl-3-nitrobenzene or simply call it 3-nitrobenzene-methyl. That is also fine. We call this 1-chloro-4-nitrobenzene or 4-chloro-nitrobenzene. If one of the two substituents is the kind that give a special name to the molecule, then the compound is named as a derivative of that special compound. If both substituents give derivative with special names, the preference is given to the substituent of the highest nomenclature priority. If you are still unsure of what is the higher or lower priority, please refer to the notes on Introduction to Organic Chemistry in my channel. Example include 2-bromophenol, 4-nitrobenaldehyde. So the aldehyde is of the higher priority. And for here is the hydroxyl. That's why we call it phenol. And for here, the higher priority given to the carboxylic acid. Alcohol is of a lower priority. So we call it 3-hydroxyl benzoic acid. Here are some other examples, like 2-chloro-ethylbenzene, or call it 1-chloro-2-ethylbenzene, 2-chloro-ethylbenzene, where the chloro was actually bonded to the ethyl, not the benzene ring. 1-chloro-ethylbenzene. Remember to bracket it. If 3 or more groups are attached to the benzene ring, the numbering is in such a way as to keep the prefix number as low as possible and with preference given to the group of the highest nomenclature priority. If one of the group present gives rise to a compound with a special name, then only 2 positions of substitution are mentioned. Now, for example, we have 2,4-dibromomethylbenzene or 2,4-dibromo-1-methylbenzene, 2-chloro-4-nitrophenol. So this hydroxyl that attached to the benzene ring is of the highest priority. Here, the highest priority will go to the OH. So it's 2,5-dichloro-4-methyl. The alphabetical order, chlorine comes first, phenol. Benzene ring is treated as a substituent and is called a phenyl group when the substituent on the benzene ring has more than 6 carbon atoms. 6 carbon atoms. The highest priority functional group is not a substituent on the benzene ring. So these are called Arene groups. Okay, so phenyl group, so we have to name a bit differently. So if this substituent has more than 6, maybe 7, so underline this for your reference. Then we have to pay attention. Then the benzene ring become a substituent. For example, we have this one. The benzene ring, we call it phenyl. So we call it 5-methyl-2-phenyl heptane. Methyl come before phenyl due to alphabetical order, but the number, okay, we follow the lower number. This is 2. This is 5. Then we have this one, 2-phenyl ethanol. Okay. We have benzyl group, then we call it benzyl bromide. All right, or bromomethyl benzene also can. Yeah, both are accepted actually. Now, benzene is a colorless liquid with a characteristic odor. It is non-polar, insoluble in water, and less dense than water. Soluble in organic solvent, so it's a good solvent to dissolve organic compounds. Here are the information regarding the freezing point and the boiling point. Like all aromatic compound, it does burn with a smoky and luminous flame due to its high carbon content. You can read this at your own time about information regarding benzene. Each of the 6 carbon atoms in benzene is sp2 hybridized, just like alkene. There are 3 sp2 hybrid orbitals and 1 unhybridized p orbital for each carbon atom, very similar to alkene. Each C atom has 3 sp2 hybrid orbitals arranged in a trigonal planar manner. 2 sp2 hybrid orbitals are used to overlap head-on with the sp2 hybrid orbital of the 2 adjacent C atoms to form 2 CC sigma bonds. 1 sp2 hybrid orbital is used to overlap head-on with the 1s orbital of the H atom to form the CH sigma bond. The benzene molecule is entirely planar. All bond angle is 120 degrees. For the unhybridized p orbital, each carbon atom has an unhybridized p orbital occupied by a single electron. Each singly filled p orbital overlaps sideways in the form of pi bonding with the adjacent p orbital on either side. The continuous overlapping of the p orbital results in a cloud of cyclic delocalized pi electrons above and below the plane of the ring. Resonance is therefore present in benzene due to the overlapping of the p orbital that produce the cloud of cyclic delocalized pi electrons. If benzene were to have a circular structure, then should be 2 kinds of carbon bonds in benzene, CC and CC double bond, but this is not the case. X-ray diffraction studies show that all the carbon-carbon bonds in benzene is actually identical and equal in length, which agree with the description of benzene as a resonance hybrid of 2 circular structures. So the electron is actually delocalized and shifting all the time. The measured carbon-carbon bond length in benzene is intermediate between the length of the CC bond and the C double bond. This shows that the bonds have partial double bond character. Experimentally, enthalpy change of hydrogenation of cyclohexene is negative 120 kilojoules per mole. For cyclohexyl 135 triene, if benzene were to really have this structure, then the expected enthalpy change should be negative 360. However, based on experimental result, the enthalpy change of hydrogenation was actually only minus 208, which is less exothermic than the expected value. So this diagram shows the potential energy of the different proposed structure as well as benzene. The cochlear structure, which contains localized pi bonds, meaning they are fixed, are not accurate representation. Instead, benzene has a structure in which the 6 pi electrons are delocalized. It is the delocalization of the 6 pi electron that confer extra stability on benzene and gave it its special aromatic character. The extra stability of benzene is reflected by the resonant energy as shown in the diagram. So this is the resonant energy, the difference between cyclohexyl 135 diene and benzene, which is the experimental data. If benzene were indeed cyclohexyl 135 triene, it is expected to undergo addition reactions that are similar to alkene. However, under the same conditions, for alkene to undergo rapid addition, benzene do not react or react very slowly. If benzene really undergoes addition reaction, its overall aromatic character, which is the delocalization of the 6 pi electron, will be destroyed, which removes the extra stability associated with the delocalization of the 6 pi electrons. Hence, the majority of reactions that benzene undergoes were just substitution in the ring, which take place with the overall retention of the aromatic character that retain the delocalization of the 6 pi electrons in the continuously overlapping p orbitals. So this is a summary of what we have gone through. Now, let's look at the reactions. The 6 pi electrons make the benzene ring electron rich and make it a source of electrons for electrophilic reagents. So we're going to talk about electrophilic substitution, where the benzene reacts with the electrophile that replaces one or more hydrogen atoms in the ring. Now, these are the examples of electrophilic substitutions: nitration, halogenation, and Friedel-Crafts alkylation, which we're going to talk about them individually. Now, the electrophilic substitution reaction of benzene is in a few steps. Number one, we have the electrophile E+ generated first. This is followed by a two-step mechanism. In step one, which is known as the slow step, this is also known as the rate determining step because it takes some time to destroy the aromaticity of the benzene ring, which means we have to destroy the extra stability that is associated with the delocalization of the 6 pi electrons in the benzene ring. In this step, the electrophile will attack the electron-rich benzene ring and remove 2 electrons of the 6 electron pi system to form a sigma bond to 1 carbon atom. The aromatic character of the benzene ring is somewhat destroyed and form a carbocation ion. This carbocation ion is resonance stabilized but not aromatic anymore. Okay, so once this carbocation ion is formed, this carbon atom here becomes sp3 hybridized, which is in a tetrahedral structure. The other 5 carbon atoms remain sp2 hybridized in a trigonal planar structure. So this is what happened. So the E was attacking the benzene ring and attach itself for the time being. And we see what come out later. In step 2, this is the fast step. So the carbocation ion intermediate loses a proton from the carbon atom that bears the electrophile. The 2 electrons that bonded this proton becomes a part of the delocalized pi electron system. This aromatic character was restored and the substituted product was formed. So this step is actually just deprotonation. So in the energy profile diagram, we can see that there was an increase in potential energy reaching the transition state. Okay, this is a slow step which explains the high activation energy. And then some energy is lost in the formation of the carbocation ion. And then towards the transition stage 2, there is energy required, but it's much lower energy. And the product form is stable, resulting in a drop in energy. So the overall reaction is still considered exothermic, okay, because the energy of the product is still lower than the reactants. So this is a slow step, and this is a fast step, which is related to the EA. So this is a summary of the reactions, reagents, catalysts, conditions, electrophile involved, and the organic product form. Now, let's start with the first one, concentrated nitric acid. Remember, concentrated. We have concentrated nitric acid and concentrated sulfuric acid mixed together to the benzene. The mixture is reflux in a water bath between 55 to 60 degrees Celsius. So we need to keep the temperature below 60 to minimize the formation of dinitrated product. We don't want more than one H substituted by the NO2 lah. So we need to control the temperature. In the nitration of benzene, the electrophile is generated from the reaction between a Bronston-Lowry and a Bronston-Lowry base. So this is a revision of what is a Bronston-Lowry acid and a base, okay? So this is the mechanism. Number one, we have the generation of the electrophile NO2+, which is the electrophile. So in the nitrating mixture, the HNO3 is acting as a Bronston-Lowry base, which means it is a proton acceptor. So it accepts the proton from the Bronston-Lowry acid, which is a proton donor, H2SO4. So HNO3 becomes H2NO3 because it accepts a proton from H2SO4. All right? And the sulfuric acid loses the proton and becomes HSO4 minus. Take note that this is a reaction in equilibrium. It's a reversible reaction. And the reaction leads eventually to the formation to nitronium ion. So the H2NO3 plus become NO2 plus with water release. As for the H2SO4, it gains the water and form HSO4 minus and H2O plus form. So in this reaction, you have the H2SO4 acting as the acid, Bronston-Lowry acid, and this one is the base. Okay. So adding this equation 1 to equation 3, we will give the overall equation to generate the electrophile. So it will be H2SO4 plus HNO3, okay? And then you have NO2 plus. So adding these three equations, you get this. And then plus 2 HSO4 minus and H3O plus. Okay. So it's better to remember these 3 steps than to memorize the overall equation. It's actually much better to know the 3 individual steps, because you also need to write these 3 equations anyway. All right. Then you derive the overall from there. The 2-step electrophilic substitution in this manner. So the NO2 plus, which is the electrophile, will attack the benzene ring. But take note, the arrow is pointing from the pi electrons towards the end. And this is a slow step. Okay, so the carbonyl ion is formed. So in this slow step, the NO2 plus acts as an electrophile to attack the electron-rich benzene ring. 2 of the 6 pi electrons in the benzene ring are used to form the CN bond. All right. Hence, the aromatic character of the benzene ring is destroyed. Okay, you involve these 2. This is the slow step. The carbonyl ion is formed. Okay, note that the carbon atom bearing the NO2 group in the carbonyl ion is sp3 hybridized. The shape with respect to this carbon is tetrahedral. The rest of the atoms remain sp2 hybridized. And then there was a loss of proton from the carbonyl ion, deprotonation. So this reaction is fast. This hydrogen return back to H2SO4, or HSO4 minus rather, to form back H2SO4, which is regenerated. Okay, another way to represent this is that you can draw the arrow from the lone pair of electrons on O in sulfate in HSO4 minus, attack the H, and then this double bond go back to restore the aromatic character. This is also fine. Now, during the nitration of benzene using a nitrating mixture, small quantities of white crystals of 1,3-dinitropentane will be formed. So you can actually form this as well. So the formation of 1,3,5-trinitropentane reacting benzene with fuming HNO2 and concentrated sulfuric acid for 5 days at 110 degrees Celsius, which is higher than the usual temperature, as mentioned. Even under this condition, the yield is only 40%. All right. Now, the reactions with halogens. So meta is a major one. In this reaction, we have the Lewis acid as the electron pair acceptor and Lewis base as the electron pair donor. Okay, let's recap what we learned under acid and bases. So again, every time we have electrophilic substitution, we must have the generation of the electrophile. Benzene does not react with chlorine or bromine in the dark. The pi electron cloud in the alkene is easily broken. However, it's not the same with arenes. The extra stability in the benzene requires use of a stronger electrophile to disrupt the pi electron cloud. So in the presence of a suitable Lewis acid catalyst like AlCl3 or FeCl3, benzene will undergo electrophilic substitution. So in a similar way, benzene also reacts with bromine with the use of a suitable catalyst. I2, F2, no. I2, 2 unreactive, and F2, 2 binary. The catalyst is thought to work by inducing polarization in the halogen molecule by accepting a lone pair of electrons. So the catalyst functions as a Lewis acid because it is an electron pair acceptor that will generate the Cl plus electrophile like this. So when the AlCl3, because the Al is electron deficient and of high charge density, so when it's brought close to the Cl2, right, it causes the Cl2 to polarize. So the lone pair electrons is attracted to Al, and during that, right, the bond pair between the covalent bond between the Cl is broken, and it undergoes heterolytic fission where both electrons that are shared between chlorine goes to chlorine. Yeah. So the AlCl3 catalyst will actually react readily with water also. So we cannot have this in conditions with water because there will be a reaction of AlCl3 with water. It's a hydration reaction. All right, to form the complex. Yeah, so it will not work in that case. So the condition has to be anhydrous in the absence of water. We also use iron fillings because it can also bring about the polarization of the halogen. Yeah, and this is how we can make the two catalysts, FeCl3 and FeBr3. Okay, looking at the reaction mechanism, we first put it side by side with the nitric acid reaction, and they are very similar. In the first step, we have the generation of the electrophile, just that for the case of halogenation, we generate electrophile of the halogen electrophile. But looking at step one, is really very similar. The carbocation ion is still formed, and then there's deprotonation as well. So very, very similar. And the regeneration of the catalyst, okay? So make sure you know the naming of the mechanism, writing the equation to show the generation of the electrophile. This must be shown, okay? And correct curly arrow, okay? Correct direction, okay? And correct intermediate, and please label the slow and fast step. These are the marking points. All right, Friedel-Crafts alkylation. Alkylation with halogen alkane and a trace amount of anhydrous AlCl3 as catalyst is often referred as the Friedel-Crafts alkylation after Charles Friedel, a French chemist, and James Kraft, who developed this reaction in 1877. Now we look at this first, then we look at the others one, okay? So alkylation means you add like maybe a methyl or ethyl, okay? So the reaction mechanism is again electrophilic substitution, and please write the equation to show the generation of the electrophile. R plus, which is the to be a methyl or ethyl, and then it will attack the benzene ring, but the arrow must be from the electron rich to the electron deficient. That is a slow step, must write the slow, must draw the carbocation ion, all right? And then you have step 2, which is the fast step, which have the intermediate product deprotonated, have the H go back and form HCl and AlCl3. As for acylation, correct? Friedel-Crafts acylation is similar to the one on the left, except that we are using an acid halide like RCOX or aromatic. This is not argon, no, this is aromatic. I need to emphasize aromatic ring. Okay. Okay, this is how we represent it, and it looks something like this. Okay, now so we don't use a halogenous alkane here, we use this acid halide. All right, it provides the acyl groups needed for the reaction. Okay, again, for both reactions, we make sure that there's no water because the AlCl3 will react readily with water. So it must be carried out in anhydrous conditions, all right? And now, following which, right, we will write the reaction mechanism is similar to the one on the left, all right? That's why they are positioned side by side so that you can see the similarity and study them together, all right? So this attack this. So what happened is that there's some polarization that causes the cell to move over. Then this becomes an electrophile attack, then break the bonds, break the delocalized pi electron system. And then you have this a join to the C because the C is the central carbon. Yeah, it's that is the electrophile part. And then the H go back, return HCl, right? Of course, there are other reactions of benzene like combustion, all right? And because of the high percentage of carbon, we expect the flame to be sooty, smoky. There's also reduction. Benzene undergoes addition reaction with hydrogen in the presence of nickel catalyst at higher temperature and pressure for alkene because of the extra energy to break the delocalized pi electron system. But there are some reactions benzene don't undergo. For example, oxidation with KMnO4, no reaction with bromine in CCl4, and no reaction with hydrogen. All right, in normal condition, not say normal, in room condition rather, it has to be carried out at very high temperature, much higher temperature and pressure even. So this one changed to orange red, not reddish brown. All right. Going on to methyl benzene, this will be the next half of the lecture. Methyl benzene is the simplest alkyne benzene with the structural formula. Methyl benzene is colorless, not soluble in water, but soluble in organic solvent. And it burns with a sooty flame with a relative high CH ratio. Now, methyl benzene has an aromatic portion and an aliphatic portion. So it makes different, these two portions will have different contributions to the chemical properties of methyl benzene. And it actually affects each other. Now, for the alkyne side chain, we will consider free radical substitution and even oxidation. For the benzene ring, we'll think about electrophilic substitution, similar to benzene, but at milder conditions. Now, we start with the side chain alkyne. So, of course, we have learned this in the previous chapter on alkane. So it's very similar. When you expose it under UV, you will have the substitution reaction taking place. So one of the H is substituted with chlorine, okay? And you have continued the substitution process by having more H substituted until all the H in the side chain are substituted. That's fine. And bromination or methyl benzene also take place at similar conditions. All right. So this is what we call free radical substitution mechanism. All right. You can just refer to the lecture on alkanes for more information. Now we have one question here before we move on. Describe the mechanism for reaction between methyl benzene and chlorine in the presence of UV light. So think about it first, then we try. So to describe the whole mechanism, please state the name first. That is a marking point. And then write down the step. Show the homolytic fission of chlorine. Make sure it's not a full arrow, it's a half arrow because it's one electron each. All right. Then you form a radical. Then move on to propagation. Okay. This one Cl minus attack this, then form CH2, then this becomes a radical. Radical, make sure the dot is at the C. Then you form HCl, and then this one attack Cl2, form Cl radical, and go on. And then termination step, the two radical meet. Two radical meet, two radical meet. Okay. Now, the benzene ring render the aliphatic side chain quite susceptible to oxidation. So the side chain can be oxidized and only a carboxylic acid remain to indicate the position of the original side chain. For example, if you have these reagents and conditions which you're very familiar with, you can actually change methyl benzene to a benzoic acid. Yes, it's possible. And the oxidation will be decolorization of the purple KMnO4 provided it's a limiting reagent. If it's not, then it will not be completely decolorized. And there will be formation of the white PPT. So this is actually white in color. All right. Benzoic acid doesn't dissolve well in water because of the non-polar benzene ring that interfere with the formation of hydrogen bond between the CO2H and the water. So the hydrogen bond between CO2H and water is not strong. So benzoic acid is not so soluble. However, if you have hot water, it will become soluble. So with cold water, it will appear as a white PPT. Okay, if you want to use alkaline instead of acid, then it will be a bit different. You have Na plus here. But the observation here will be similar, except that because you're using alkaline KMnO4, you expect MnO2 to be produced instead of Mn2 plus, you have MnO2 because without the acid. So you form a brown-black PPT. This is a brown-black. So it's actually black but brownish. But the white PPT of benzoic acid still form upon cooling and acidification. Because remember, this is Na+, so you need to acidify it to turn it back to benzoic acid. However, this no reaction with the potassium dichromate. Now, so for stoichiometric calculation, the equations are required to derive the ratio of the oxidizing and the reducing agent. So this is the oxidation half equation in the above reaction. You have learned some of it in the first topic on stoichio, how to balance equation like this. So you have a water here, balanced with a H plus, and the H plus is here, so you have the electron to balance H plus, the charge. And then this is the famous MnO4 minus equation. MnO4 minus, Mn2 plus, then because it's an oxidizing agent, so it's reduced itself. So it gain electron, it's acidified, so water put here, then you balance. Then you just add these two together by balancing the number of electrons. So what happens is that to combine these two, you can add you times 5 here, and you times 6 to balance the electron to be 30, which explains why you have 5 here. And the water should be 10, but here becomes 24. 24 minus 10 give you 14 over here. All right. Then here is 6 because of the 6 here. Then here is 18 because by right 8 times 6 48, but you have another 30 here. So 48 minus 30 give you back 18. Here 5. Then here 6 and 14 as mentioned just now. Now, ethyl benzene or other benzene derivative will also produce benzoic acid. So the rest of the alkyne group, what happened to them? Just destroy and form CO2 and water. Yes, this is important. So the rest of the alkyne side chain, right? Sorry, they all form carbon dioxide water. You just lost it. You just lose it. Yeah. You form a lot of CO2 and water. No choice. Okay. So this is important. Same product, benzoic acid. No matter how long is the alkyne chain. Okay. So the formation of the carboxylic acid will tell you the position of the alkyne side chain. But it can't really tell you what is the what was it previously, unless you go and count the amount of CO2. So if you know the number of moles of CO2, then you can actually count back to see what is the original number of carbon atoms in the alkyne side chain. All right. So alkyne benzene without a H atom bonded to the benzylic carbon atom do not undergo oxidation when heated with acidified KMnO4. Yes. No. Okay. So in this case, sorry, no. Must have at least one hydrogen atom bonded to it, like bonded to CH3. But here the nothing what. It doesn't. The alkyne benzene without a H band, there's no H atom. This is important. There's no H. Okay, do I have to know the actual reason in the syllabus? No H atom bonded to the carbon atom, forget it. It won't, full stop. Okay, try. So this is, you can cover the answer first and try yourself. Ignore the balancing, all right? So, no reaction. Yes, because you have a H here. Wait, there is, right? Yeah, no, can. This one cannot. Because no H bonded to the benzylic carbon atom. Yeah, here got no H at all. So cannot. Here at least got one H here. So at least you have a H here. So still can. Here, right? No H. Here got H. So here will be COH. COH. Here remain. Then here no change. Here double bond. Here will also become COH. But you must indicate how many CO2. So this one becomes CO2. This part come out. All right. Now next, identify the reactant of the reaction. Okay, fine. For this one, right? Identify the reactor. So what is this? So you work. This one is working backward. So they give you this. So you identify back lah. So it could be, because C10 ma. So out of 10, right? 6 must be the benzene ring. So left with how many? 4. So here is 1, 2, 3. Then there's one extra one. So there are 3 possible structures. I cannot pinpoint which exactly, but it's just possible. So will be either this 1, 2, 6, 7, 8, 9, 10. It will be either here or maybe here or this one. Possible, right? Yeah, can be this one. So the CO2 come out. Yeah, because it's not balanced, so it could be 2 here, you see. Here, very ambiguous. So here will be COH. Anyway, these 2 pladite must be COH lah. Okay. Now, after looking at the alkyne side group, look at the benzene ring itself. All right. So as covered, the benzene ring undergoes nitration, Friedel-Crafts, and halogenation, right? Under the mechanism of electrophilic substitution. So the conditions are, the reaction mechanism is quite similar, but the conditions are milder. Okay, so if we have a methyl benzene, right, undergoes nitration, you just have the reaction at 30 degrees Celsius. Let's compare what is happening previously. In the previous reaction mechanism on this one, right? The condition is a bit more extreme, 55 degrees Celsius. But when you go to the methyl benzene, it's 30 degrees. It's almost like room temperature, right? But the reactants and the catalyst is the same. Okay, so you can form this again. But in this case, right, you can either form 2, 4. The minor product will be the 3 actually. Auto, meta, para. The meta one will be the minor. As for halogenation, definitely faster rate of reaction compared to benzene itself. But you still form this 1, 2, and 4. Again, 3 is the minor product. All right, so if you look at the previous one on just benzene alone, yeah, they only talk about 1. Yeah. Not so much focus on which side because it doesn't matter, right? Yeah, but for here, because of the CH3, right, the position of the substituted halogen and NO2 become important. All right. The presence of the CH3 group in methyl benzene affect the reactivity and the orientation of the electrophilic substitution. So let's see. The lower temperature is used for the nitration of methyl benzene, whereas nitration of benzene requires a higher temperature. So this shows that methyl benzene is more reactive, and CH3 is said to be an activating group. As for orientation effect, the major product, as you can see, is 2-nitromethyl or 4-nitro, not 3. So the substitution by the NO2 is occurring chiefly at the 2 and 4 position relative to the CH3 group. So we call it 2,4 directing, auto and para, not meta. Now, when the electrophilic reagent attacks the aromatic ring, it is the group already attached to the ring that determines how readily the attack occurs and the position of substitution. Reactivity in electrophilic substitution depends on the tendency of the substituent group to release or withdraw electrons. So a group that donates electrons or delocalizes electrons activate the benzene ring towards electrophilic substitution. But if we have a group that withdraws electron, it will deactivate the benzene ring. So an activating group is electron donating. It increases the electron density and makes the ring more susceptible to electrophilic attack, which helps to disperse the positive charge in the intermediate carbocation ion. So when you want to make the carbocation ion stable, you say disperse the positive charge with the help of the electron donating group that's attached to the ring. So the group attached to the benzene ring is activating as it activates the ring towards electrophilic attack. So these are the examples, CH3, NH2, and OH. So they are donating their electrons, all right, to the ring and stabilize the carbocation ion by dispersing the positive charge. Whereas a deactivating group, right, is electron withdrawing. It will increase the electron density in the benzene ring and make the ring less susceptible to electrophilic attack. So instead of dispersing, it will intensify the positive charge to the carbocation ion and destabilize it. The group attached to the benzene ring is classified as deactivating. If it deactivates the benzene ring to make the ring less reactive than benzene towards electrophilic substitution. Examples is like your NO2, COH, Cl. They withdraw electron because of their high electronegativity. All right. So if Y is the electron donating group, the rate of reaction will be the highest. If Z is the electron withdrawing group, it will be the lowest. So methyl benzene is more reactive because this is the explanation. You must say CH3 is electron donating, activating group, increase electron density in the ring, make it more susceptible. Can ready. So this is a list of activating and deactivating groups on the benzene ring and the difference in conditions, all right, to show you how it works out. So this is just benzene alone, and we have the conditions as such. And this is methyl benzene. We have, OH, even more activating. So you just have it at room temperature, even without any catalyst. We have a deactivating group here, higher condition, more extreme conditions, and we have even worse, NO2. So this is the order of the reactivity of the different substituent effect on the benzene ring towards electrophilic substitution. And the products form is also different. All right, this is all reference to nitration reaction of the benzene ring, 2,4. For deactivating, right, for the Cl is still 2,4, but comes to the NO2, it will be 3, strangely. Yeah, that is for you to take note only. Now, the substituent on the benzene ring donate or withdraw electron through inductive and resonant effect. So inductive effect is the donation or withdrawal of electron through sigma bonds due to electronegativity difference. For example, CH3, alkyne groups have a sp3 carbon. Since sp3 carbon has less S character. Okay. Uh, electron actually are not so tightly held lah, and more easily donated. So the it's not holding on to the electron, so it can actually donate this electron to the benzene ring. So this substituent is said to be electron donating by inductive effect. Okay, so that's called inductive effect. However, the opposite is true. If we have an electron withdrawing group like Cl, which is highly electronegative, they will pull electron density away through sigma bond. So this substituent is said to be electron withdrawing by inductive effect. Resonant effect is different. It's the donation or withdrawal of electron through pi bonds due to the continuous p orbital overlap. So the way they interact is different. Inductive is through sigma, resonant through pi. Okay. Now, for OH is a good electron donating group, right? So it will, because it has a lone pair of electrons on the atom. So the lone pair is in the p orbital and it can be easily delocalized into the ring. Okay, this is called resonant effect. However, if we have C double bond O carbonyl and NO2, they are directly attached to the benzene ring by the atom that is doubly or triply bonded. All right. In this case, the pi electron of the ring can be delocalized because now it's like they are electronegative, right? Because of the O here is the N and O. So the electrons in the pi bond system of the ring, right, can go into them. You know what I mean? So it's actually the electron can move towards this substituent through the pi electron system, through this p orbital overlapping, through the pi bonds in the p orbital overlapping. So the substituent is said to be electron withdrawing. Now consider chlorobenzene and phenol, where there's competition between electron withdrawing and electron donating. Then how do we explain? So by inductive effect, cell atom is electron withdrawing. Okay, here. But by resonant effect, right, the lone pair of electrons can interact with the delocalized pi electron cloud system of the benzene ring. It can interact through the pi bond and delocalize. So increase electron donate density. So it's like very strange. One is inductive, one resonant. So there's this conflicting issues here. But in this case, right, we just treat. In this case, right, the fact is inductive effect is actually stronger because chlorine, right, is in period 3. So the p orbital are actually more diffuse. Yeah, leading to a less effective side overlap with the p orbital. So if we have a more diffuse p orbital, the overlapping is not so good. So the effect of the electron withdrawing is weakened. So the electron donating effect is weakened, but electron withdrawing effect is relatively strong. So this will actually decrease electron density and it makes the ring less susceptible. So it's a deactivating group. That's why Cl here is deactivating, but not a strongly deactivating one. But in the case of this, there's another reason, like the O is more electronegative. So the OH group electron withdraw, but the lone pair of electron on O can interact with the delocalized pi electron cloud. Okay, so here is electron donating, here is electron withdrawing. How? But OH is electron donating, correct? The resonant effect is stronger because here, right, is the, where is it, period 3, but oxygen period 2. So the p orbital is less diffuse. So the overlapping, okay, of the p orbital of oxygen is more effective with the p orbitals of the benzene ring. Okay. Yeah, something along that line. Okay, so the overall effect of the OH group in phenol is electron donating. Okay, something to do with okay, O period 2. So more effective overlap. Should say side-on overlap with the p orbitals of the benzene ring. Now, let's go and look at orientation. The substituent group in the benzene ring not only activates or deactivates the ring, it also controls the position of entry of an incoming group. So we come and explain this. Depending on the position it directs an incoming group to, a substituent group can be classified as 2,4 directing or autopara or 3 directing meta. For 2,4 directing group, the electrophile attack chiefly at the 2 and 4 position. So it direct incoming group to 2 and 4, like NH2, OH, CH3, and even Cl. But a 3 directing group causes an electrophile to attack chiefly at 3 position relative to it. So it directs the incoming group mainly to the 3 position relative to it, like NO2, COH, and CHO. Don't have to know the reason. Just remember this. Okay, the data booklet will actually summarize this, so there's no need to memorize. Okay. So for here, these are the substituent group that have a 2,4 directing effect. Okay, they are all activating groups, although some are not so strong. So each substituent here has a lone pair of atom that's bonded to the carbon atom of the aromatic ring. Okay. Each substituent can therefore donate electrons by resonant effects, delocalize electrons into the ring. All right. Then for the weakly deactivating to all the way to strongly activating, don't have to memorize all they just know 2, 4, except for these three. These groups is 3 directing. So the halogen atoms are different from the other substituent. All right. Okay. The inductive effect is stronger here. Okay. Then resonant effects. Okay. For here, each substituent is unsaturated and does not have an atom with a lone pair bonded directly to the benzene ring. Yeah. So the electron withdrawing lah. So this is the summary of the deactivating groups and the activating groups. If there are 2 substituent groups in the benzene ring and their directing effects oppose each other, directing effect of the more powerful activating group wins. Okay, so for example, we have this and this, right? Both groups will direct to the same position, 2. Then 1, 2, 1, 2, position 2. 1, 2, 3. Yeah, we do 3 in this case because NO2 is 3 directing. Then CH3, yeah, it's also 3 directing. 2. Both groups, 3 directing, 2, 4 directing. So here. So this is good because from this perspective, here is 2, from here is 3, so good. But what if opposing, like 1 is CH3, 1 is Cl, then the one that is stronger will be the CH3. Yeah, because this is 3 from this perspective, but here is 2 from this, so okay. So because Cl, right, is only considered weak, but CH3 is also activating. Let me see. Oh, yeah. Activating group. Yeah, activating group wins. So this is the activating group, so follow. Because if both activating and deactivating group, just follow activating. So the order to which the various substituents are introduced to the ring is important. For example, in this example, right, suggest reagents and conditions for the synthesis of 2-bromo-nitrobenzene from benzene. A, so you have Br, so it had to be Br2 rather. Okay, if a halogenation, I thought it's Br2. Okay, so this one is here, Br2. Yep. In this, and this is 2-4 directing, 2, 3, 4, 2 here. So it can be here, 2-4 directing. So we concentrated nitric acid and sulfuric acid and heat with 2 or 4. But if you have something like this, you have NO2, 3, the 3 directing, will form this. Because this is wrong, because the answer is asking for 2-bromo nitro. This is not 2-bromo nitro, so this is wrong. So it's important to know the order. Is it Br2 first or nitration first? Halogenation first or nitration first? Now, if they said, okay, make 3 nitrobenzoic acid like this, which one is first? So if you do, it should be oxidation of this first, and then you add the NO3 because this is 3 directing. Next, COH is 3 directing. You can look at the data booklet for reference. Then if what happens when the 2 synthesis steps are swapped, then you get the wrong answer. You won't get 3 nitrobenzoic, you get 2 or 4 because of the different directing groups. Yeah. It will direct differently. All right. So this is a summary of the reactions of benzene as well as methylbenzene, and a summary of the electrophilic substitution, how to write the mechanism. And that's it for today. Optional reading not tested. So that's it. Thank you. I hope you will subscribe to my channel. Bye-bye.